On March 26, 2016, a $273 million Japanese space telescope called Hitomi was 5 weeks into its mission, orbiting Earth and scanning distant black holes with some of the most sensitive X-ray instruments ever built. Then it passed over the South Atlantic. At 3:01 in the morning Japan Standard Time, while the spacecraft crossed a specific patch of sky between South America and Africa, its inertial reference unit suddenly reported a false rotation of nearly 22 degrees per hour. The spacecraft was perfectly stable, but the onboard system didn't know that, so it fired the reaction wheels to compensate for spin that didn't exist. Then a thruster kicked in with a misconfigured software setting, making everything worse. Within hours, the spacecraft was spinning so fast that its solar panels and extendable optical bench ripped clean off the body. 5 weeks of operation, $273 million, gone. JAXA's investigation ultimately traced the root cause to an attitude control software error. But the failure sequence began in one of the most radiation-hostile zones in low Earth orbit, a region where spacecraft designers know sensor glitches are far more likely. That region is the South Atlantic Anomaly, a patch of sky where Earth's magnetic field is so weak that the inner Van Allen radiation belt dips unusually close to orbiting spacecraft, bathing their electronics in energetic trapped particles. NASA, ESA, and every major space agency on Earth knows about it. They plan around it. They lose sleep over it. Hitomi is not an isolated case either. The Globalstar satellite phone constellation, orbiting at about 1,400 kilometers, suffered so much cumulative radiation damage from repeated SAA passes that the company warned investors in SEC filings that by 2008, substantially all of their in-orbit satellites would lose the ability to support two-way communications. SpaceX's first Dragon cargo capsule on the CRS-1 mission in October 2012 experienced a flight computer glitch that the ISS program manager publicly attributed to a suspected radiation hit. And the Hubble Space Telescope, it physically flies through the South Atlantic Anomaly up to 9 times per day and avoids taking any science or calibration observations during those passages, losing 20 to 25 minutes of usable time per pass, with 7 to 9 impacted orbits in a row before it gets a clean stretch of sky. So why does almost nobody outside the space industry know this thing exists? And why is it getting bigger? To understand what's happening above the South Atlantic, you need to understand what's supposed to be happening everywhere else. About 2,000 miles beneath your feet right now, there is a churning ocean of liquid iron and nickel, roughly the size of Mars itself. It is hotter than the surface of the sun, and it is moving constantly. As Earth rotates, that molten metal generates massive electrical currents, and those currents produce a magnetic field that wraps around the entire planet like an invisible force field extending tens of thousands of miles into space. Scientists call it the magnetosphere. Along with the atmosphere, it is one of the key reasons Earth has stayed habitable over billions of years. Every single second of every day, the sun blasts out a stream of charged particles called the solar wind, moving at roughly 1 million miles per hour. Without the magnetic field deflecting that wind around the planet, those particles would gradually strip away Earth's atmosphere, molecule by molecule, over geological time. Mars likely lost much of its early atmosphere partly this way. After its iron core cooled and its global magnetic field faded roughly 4 billion years ago, the solar wind could strip atmospheric particles far more easily. Today we can see the result in the thin, wispy remnants of the Martian atmosphere, less than 1% the density of Earth's. So Earth's magnetic field is not some abstract physics curiosity filed away in a textbook. It is the invisible wall between a planet with oceans and forests and a dead, irradiated rock. And that wall is getting thinner. In November 2013, the European Space Agency launched 3 identical satellites called Swarm from the Plesetsk Cosmodrome in northern Russia aboard a Rokot rocket. Their mission was simple but wildly ambitious: map Earth's magnetic field with more precision than any instrument had ever achieved. Each satellite carried a vector field magnetometer, an absolute scalar magnetometer built by the French Atomic Energy Commission with accuracy better than 0.3 nanotesla, plus star trackers, accelerometers, electric field instruments, and GPS receivers. Over the next decade and counting, Swarm has built the longest continuous absolute accuracy space magnetic record in history, surpassing even the decade-long CHAMP mission that came before it. What Swarm found over that period made headlines, at least in scientific journals. The mainstream press barely noticed. The global magnetic field has weakened by roughly 9% since scientists first began measuring it reliably in 1840. That number comes directly from a 2016 paper published in Nature Communications by Finlay, Julien Aubert, and Nicholas Gillet, titled Gyre-Driven Decay of the Earth's Magnetic Dipole. It is not an estimate or a projection, it is a measurement. Going further back, archaeomagnetic data pulled from ancient pottery, fire hearths, and brick kilns shows approximately 30% decline over the past 2,000 years. The current rate of decline sits at about 5% per century, or roughly 16 nanotesla per year. Now those numbers sound alarming, and honestly, they are worth paying attention to. But here is the part that most doomsday channels on YouTube consistently leave out, and it changes everything. Earth's magnetic field right now is still roughly twice as strong as its average over the past 5 million years. A 2015 study led by Huapei Wang at MIT, published in the Proceedings of the National Academy of Sciences, put it directly. Today's field intensity is approximately double the planet's long-term average. Even at the current rate of decline, the field would need about 1,000 years just to fall back to normal. Not to zero, not to dangerous, just to its historical average. So yes, the field is weakening. That is absolutely real. But it is weakening from an unusually strong peak. Context matters. Now here is where the story gets genuinely wild, because the really interesting part is not the global average. It is what is happening regionally. And the South Atlantic Anomaly is where this goes from interesting geophysics to, okay, we might actually have a problem. The SAA sits roughly between South America and Southern Africa, centered near the coast of Brazil at about 27 degrees south, 49 degrees west. Inside this zone, the magnetic field intensity is dramatically lower than the surrounding areas. Swarm data published by Finlay, Kloss, and Gillet in a 2025 paper in Physics of the Earth and Planetary Interiors showed that the minimum field intensity inside the anomaly dropped from 22,430 nanotesla in 2014 to 22,094 nanotesla in 2025. And the total area of weakened field, measured as the zone below 26,000 nanotesla, expanded by 0.9% of Earth's entire surface area in just 11 years. That is roughly half the size of continental Europe in a single decade. And then came the part that genuinely surprised the scientists studying it. In May 2020, ESA announced that the South Atlantic Anomaly appeared to be splitting into two separate lobes. A second center of minimum intensity had emerged southwest of Africa, and it was developing rapidly. Jürgen Matzke at the GFZ Potsdam Research Center in Germany went on the record stating that a new eastern minimum has appeared over the last decade, and in recent years is developing vigorously. Geophysicists do not use the word vigorously unless something has genuinely caught their attention. Finlay at the DTU Space in Denmark, the lead author on the key Swarm papers, gave what might be the most honest pair of statements any scientist has offered on this topic. He said that there's something special happening in this region that is causing the field to weaken in a more intense way. Then, in the same set of interviews, he added that they know from paleomagnetic records that Earth's magnetic field has weakened many times in the past, displaying regions like the SAA without reversing. Both of those statements are true. Both matter equally. Hold them together. The International Space Station makes this very concrete. The station orbits at about 410 kilometers altitude and passes through the SAA on roughly 5% of its total orbits. According to published radiation studies, that 5% of orbital time accounts for a disproportionate share of the station's total radiation exposure, potentially more than half. Crew members absorb between 0.2 and 0.5 millisieverts per day in orbit, and during SAA crossings, astronauts regularly report seeing bright flashes of light with their eyes closed, caused by cosmic ray particles passing directly through their retinas and optic nerves. These are called phosphenes. Mission planners generally avoid scheduling spacewalks during SAA transits to limit crew radiation exposure. Meanwhile, on the other side of the planet, magnetic north is putting on its own performance. The magnetic North Pole, the spot your compass needle tracks, used to drift slowly at maybe 15 kilometers per year. Then around 1990, it started accelerating. By 2017, it was sprinting toward Siberia at over 55 kilometers per year. It was moving so fast that the World Magnetic Model, the reference standard that governments, militaries, airlines, and every smartphone compass on Earth relies on, had to be updated a full year ahead of schedule in 2019. A paper published in Nature Geoscience by Livermore, Finlay, and Bailiff traced the acceleration to a battle between two negative magnetic flux patches deep on the core mantle boundary. The Canadian patch is weakening. The Siberian patch is winning. So the field is weakening globally, collapsing regionally over the South Atlantic, splitting into two lobes, and magnetic north is racing across the Arctic at highway speed. These are not theories or speculation. These are measured, published, peer-reviewed observations from the world's leading space agencies and geophysics departments. Which brings us to the question everyone actually wants answered. Are the poles about to flip? Around 41,000 years ago, something remarkable happened. Earth's magnetic field didn't just weaken, it collapsed to roughly 5% of its peak strength and briefly reversed polarity entirely. North became south, south became north. Geologists call this the La Champ excursion, named after lava flows in the Chêne des Puys region of central France, where Bonhomet and Babkin first discovered the reverse magnetism in 1967. Black Sea sediment cores analyzed by Novacek and colleagues, published in Earth and Planetary science letters, showed the fully reversed phase lasted about 440 years, centered on 41,000 years before present. Speleothem evidence pinned the broader excursion envelope to roughly 42,250 to 39,700 years ago. In 2021, a team led by Alan Cooper published a dramatic paper in Science arguing that this magnetic collapse triggered a cascade of environmental consequences. Using radiocarbon data from ancient New Zealand Korte trees, among the oldest trees on the planet, they linked the La Champ event to ozone layer depletion, shifts in wind belts, expansion of ice sheets, and possibly even the extinction of Neanderthals and Australian megafauna. They coined a name for it, the Adams Transitional Geomagnetic Event, a nod to Douglas Adams and the number 42 from the Hitchhiker's Guide to the Galaxy. That paper got enormous press coverage. It's a great story, but the scientific response was more complicated than the headlines. Within months, formal critiques appeared in the same journal, Science. Paleoanthropologist John Hawkes challenged the Neanderthal extinction timeline, arguing the dating evidence didn't actually align with the magnetic event. A team of heavyweight researchers, including Jean-Jacques Hublin and Chris Stringer, two of the most respected names in human evolution, questioned whether the data actually supported the causal connections the paper claimed. And Monica Korte at GFZ Potsdam stated separately that they found no evidence suggesting the La Champ event affected life on Earth, because the atmosphere itself provides significant shielding against cosmic rays, even when the magnetic field is weakened. The honest answer is this: the La Champ excursion was real and dramatic at the planetary scale. Whether it actually harmed living things is genuinely contested among the best researchers in the field. That is not a dodge. That is the actual state of the science as of 2026. As for whether a full reversal is happening now, the scientific consensus is remarkably firm. In 2018, a paper in PNAS by Brown, Korte, Holm, Wardinsky, and Gunnarsson compared today's field geometry to similar weak field structures at 49,000 and 46,000 years ago, periods that featured SAA-like regions. Neither led to a reversal or excursion. Their conclusion was that the current weakened field will also recover. The USGS states officially that predicting a reversal based on the current state of the field is extremely difficult, and for all we know, the field may actually get stronger. But here is where I need you to hold two ideas in your head at the same time, because both of them are true. The poles are probably not about to flip, and a weakened magnetic field still makes us more vulnerable to something that is absolutely, definitely going to happen again. A massive solar storm. On September 1st, 1859, British astronomer Richard Carrington was sketching sunspots through his telescope at his private observatory when he witnessed something no scientist had ever documented before. A blinding white light flare erupted from the surface of the sun. The resulting coronal mass ejection, a billion-ton cloud of magnetized plasma, reached Earth in just 17 to 18 hours. Normal transit time is 3 to 4 days. This CME was traveling at over 2,500 kilometers per second. When it hit, the results were spectacular and terrifying in equal measure. Auroras lit up the night sky as far south as Cuba, the Caribbean island of Tobago at just 11 degrees north of the equator, Colombia, Hawaii, and southern China. In the Rocky Mountains of Colorado, gold miners woke up and started making breakfast at 2 in the morning because the aurora was so bright they genuinely thought it was dawn. Telegraph systems across Europe and North America went haywire. Operators received painful electrical shocks from their equipment. Some stations caught fire. And here is the detail that should genuinely unsettle you. Multiple telegraph lines continued transmitting coherent messages with their batteries completely disconnected, powered entirely by the geomagnetically induced currents surging through the wires themselves. In 1859, the most sophisticated electrical infrastructure on the planet was copper wire strung between wooden poles. Today, it is everything. Power grids spanning entire continents, telecommunications networks, GPS satellite constellations, the internet backbone, water treatment and distribution, hospital life support systems, financial markets processing trillions of dollars per day. Lloyd's of London commissioned a study with atmospheric and environmental research in 2013 to model what a Carrington-class storm would do to the modern North American power grid. Their findings were staggering. Between $0.6 and $2.6 trillion in total economic damage. 20 to 40 million Americans without electrical power for periods ranging from 16 days to 1 to 2 years, depending on transformer availability. In one severe modeled scenario published in Space Weather by Otten and colleagues in 2017, daily economic losses from a space weather blackout could reach $41 billion if 66% of the US population were affected. That figure represents roughly 100% of daily American GDP. We have already seen smaller previews of what this looks like. On March 13th, 1989, a geomagnetic storm slammed into Earth and collapsed Hydro-Quebec's entire electrical grid in under 90 seconds. 6 million people lost power for 9 hours in the middle of a Canadian winter. A single damaged transformer at the Salem Nuclear Generating Station in New Jersey cost $12 million to replace. The Halloween storms of October 2003 destroyed Japan's multi-million-dollar ADOS-2 environmental satellite, forced ISS astronauts into the radiation shelter module, and caused at least 12 transformer failures across South Africa. And in May 2024, the Gannon storm became the first G5-class geomagnetic event in over 20 years. Aurora appeared across the entire continental United States, and GPS-guided John Deere tractors across the American Midwest veered off their programmed paths, costing affected farming operations thousands of dollars each. None of those events were anywhere near Carrington's scale. On July 23, 2012, a coronal mass ejection, at least as powerful as the Carrington event, ripped through the exact point in Earth's orbit that our planet had occupied just 1 week earlier, 7 days. That is the margin by which modern civilization avoided a potential trillion-dollar catastrophe that most people on Earth have never even heard of. Daniel Baker, director of the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder, analyzed the 2012 event with his team and published the findings in the journal Space Weather. His statement has been quoted by NASA ever since. If it had hit, we would still be picking up the pieces. In my view, the July 2012 storm was, in all respects, at least as strong as the 1859 Carrington event. The only difference is it missed. Pete Riley, publishing in the same journal, ran the probability analysis and estimated with acknowledged uncertainty roughly a 12% chance of a Carrington-class event striking Earth in any given decade. 12% per decade. Think about that for a second. If you're finding this useful, hit subscribe. I cover space and science stories like this every week, and there's a lot more coming. Now, there is one more piece of this puzzle, and it is the reason this topic has exploded across certain corners of the internet in recent years. A YouTube channel called Suspicious OB Servers, run by a man named Ben Davidson, has spent years promoting something called the solar micronova hypothesis. The core claim is that the sun periodically undergoes a partial nova-like eruption, roughly every 12,000 years, supposedly triggered by Earth crossing a galactic current sheet. Another promoter, Douglas Vogt of the Diehold Foundation, names 2046 as the specific year of the next event. Davidson's framing is vaguer but equally alarming, suggesting the event could come within decades, with civilization-ending consequences. Here is what you need to know, and I want to be precise about this. Micronovae are a real, observed, peer-reviewed phenomenon in astrophysics. In April 2022, a team led by Simone Scaringhi at Durham University published a paper in Nature titled Localized Thermonuclear Bursts from Accreting Magnetic White Dwarfs. They documented the first 3 confirmed micronovae, observed using NASA's TESS space telescope on 3 white dwarf stars designated TV Columbae, EI Ursae Majoris, and Assassin 19BH. These are genuine thermonuclear explosions. Co-author Paul Groot at Radboud University described the mechanism clearly. Hydrogen fuel gets contained at the base of the magnetic poles of some white dwarfs. This leads to micro-fusion bombs going off, which have about 1/1,000,000th of the strength of a nova explosion, he said. But here is the critical detail that Davidson's model ignores entirely. Every single confirmed micronova has occurred on an accreting magnetic white dwarf in a binary star system. A white dwarf is a dead, ultra-dense remnant of a star that has already burned through its fuel. In a binary system, the white dwarf actively pulls hydrogen from a nearby companion star. That stolen material spirals in, gets funneled to the white dwarf's magnetic poles, builds up in a thin layer, and eventually reaches temperatures and pressures high enough for brief thermonuclear fusion. The Sun is a single, main sequence, hydrogen-fusing star. It has no binary companion. It has no accretion disk. There is no known mechanism in solar physics for the Sun to undergo this kind of white dwarf accretion process. Astronomer Phil Plett, writing in Bad Astronomy, pointed out that a true micronova-scale energy release occurring on the Sun would produce enough output to severely damage or sterilize the planet. The deeper issue is not Ben Davidson's credentials, though he holds degrees in economics and law rather than any physical science. The real problem is that the proposed mechanism simply does not match how observed micronovae actually work. Now, here is the thing I want to be honest about, because I think this matters. The people who find Davidson's content compelling are not fools. They are responding to real signals. The magnetic field is weakening. The South Atlantic Anomaly is expanding and splitting in real time. Magnetic north has been racing across the Arctic. Carrington-class storms are a genuine, quantified, peer-reviewed threat. All of those things are absolutely true, and every single one of them comes from the same scientific literature that mainstream geophysicists cite. The disagreement between fringe and mainstream is not about whether something is happening. It is exclusively about timing, mechanism, and severity. Mainstream geophysics says the field has weakened many times before and recovered without reversing, and that the Sun is structurally incapable of producing a micronova. The fringe says civilization is on a countdown clock to a catastrophic reset. One of those positions is supported by 150 years of continuous geomagnetic measurement, millions of years of paleomagnetic data, and direct satellite observation by 3 space agencies. The other is built on a misapplied astrophysics paper and YouTube content with high production values. So what is NASA actually saying about all of this? In August 2020, NASA Goddard published a release titled "Researchers Track Slowly Splitting Dent in Earth's Magnetic Field." It acknowledged the SAA's westward expansion, its recent splitting into 2 lobes, and its documented impact on satellite operations. NASA geophysicist Weijia Kwang explained that the observed anomaly can be interpreted as a consequence of a localized reversed polarity field growing strongly in the SAA region. Think about that sentence for a second. A NASA scientist is telling you, on the record, that there is a patch of backwards magnetic field growing inside the Earth beneath the South Atlantic. In August 2021, NASA JPL's Alan Buas published a more pointed article directly addressing fringe claims. It stated clearly that paleomagnetic studies show the field is about as strong as it has been in the past 100,000 years and is twice as intense as its million-year average. NASA Langley scientist Martin Mlinjak, when asked about the pole flip cataclysm theory that had been circulating on Joe Rogan's podcast, responded with 2 words: total bogus. Is NASA hiding something? There is no credible evidence of that. They actively publish the data sets, the satellite archives, the scientific visualization animations, and they give on-record interviews to journalists. What is fair to say is that NASA tends to communicate in a softer register than ESA. NASA describes the South Atlantic Anomaly as a small but evolving dent. ESA calls it a growing weak spot, where the field is weakening in a more intense way. Both agencies are describing exactly the same swarm satellite data. The difference is institutional communication style, not concealment, not conspiracy, just different approaches to talking to the public. And that, honestly, is the most interesting part of this entire story. The real tension is not between scientists and conspiracy theorists. It is between a magnetic field that is still historically strong, but weakening regionally at speeds that genuinely surprise the researchers measuring it. Between infrastructure that handles small geomagnetic storms without issue, but has never been stress tested against a true Carrington recurrence. Between credentialed, respected scientists like Daniel Baker at the University of Colorado, publicly warning that a direct hit would leave us picking up the pieces for years, and those very same scientists saying with equal confidence that the poles are not about to flip and the sun is not going to explode. That gap between real, documented, quantified concern and imagined catastrophe is where the honest, credible story lives. Earth's magnetic field is not about to vanish. The poles are almost certainly not about to reverse. The sun is not going to micronova. But some regional changes, especially the SAA's evolution and magnetic north's rapid drift, have been surprising enough to force updates to operational models ahead of schedule. The South Atlantic Anomaly is growing and splitting in real time, tracked by 3 ESA satellites circling the planet 16 times every single day. Magnetic north is currently in Siberia and still moving. The next Carrington-class solar storm is not a question of if, it is a question of when, and whether the power grid under your feet right now will be ready for it when it comes. As of 2026, ESA's Swarm constellation is still up there, still orbiting, still measuring every fluctuation. The data keeps coming in, and this story is not over, not even close.